Oh, this is so difficult. John Daintree cheered me up a day or so ago. We were saying how stressful it is to talk at these conferences, and we were trying to cheer each other up. And he said, one of the things you've got to bear in mind, for instance, is actually, everybody's on your side. We're friends, we know each other, so that's a good thing. And the other thing that he said is, at least when you're talking at these things, you have the comfort of knowing that you know more about the subject than the people you're talking to. And this is just not the case tonight. And what I'm going to do is soften you up a little bit with regards to complex numbers. In the next version of Dyalog, version 13, we will be introducing complex numbers, complex arithmetic. And so I just want to plant the seed and convince you that they're cool and good things to have. And my background, I have just a bachelor's maths degree from, I went to college with Pythagoras. It's a long, long time. We had sticks in the sand and stuff. And that was really the last time I looked at complex numbers until about 18 months ago. This was before we decided to do this project, and I was just, it's lovely when you're not in an educational program and you have the luxury of time just to explore areas that you rushed when you were at college. It's wonderful. And I explored the complex numbers again, and I sort of fell in love with them. They're beautiful, wonderful things. One of the difficulties, and it's just sort of gradually catching up with the internet age, is that what's really strange now is the knowledge is just all out there, and the difficulty is filtering it and knowing what to pick and choose. Because the first thing I did when I was volunteered to talk about this was to think, you think you know something, and then when you have to actually talk about it, then you better do some research. And the first port of call is, say, Wikipedia. It's like a kiddie in a sweetie shop. You look at this page, and then you see that, and you click on that. And there's just an overload of information. Your head explodes with all of the possibilities of the history and the wonderful things you can do and the applications. So I got a bit overloaded. What I managed in the end, what I'll do is I'll recommend, I found these 4 reference sites, if you like. If you're interested in what I have to say, or if I can set a spark that makes you go and revisit your university notes. There's an excellent paper by Paul Penfield, who some of you may have been in APL long enough to... Did anybody go to the 81 conference and hear this? Anybody's... I can't remember when it is. It's an odd year. It was... You went... San Francisco. Was it San Francisco? And this is just a superb paper where there's been so much work put into... describe complex arithmetic as it would be applicable to APL. And I believe Eugene MacDonald had a big, Bob was telling me, big part to play in this. So some really very creative, wonderful people produced a proposal for complex arithmetic in APL. And this was adopted by a number of vendors. Who did complex numbers first? Was that Sharp, or did it APL? I think Sharp did.
Either APL 2 or Sharp.
Yeah, certainly APL 2 had. Okay. That would have been before APL 2 because that didn't come out till a little later. And this made it into the extended APL standard, which is the second reference document, and they changed a couple of things from Penfield's original proposal, but largely it is as that paper was described. The thing that I really, there's a book by Roger Penrose, I don't know if you've seen this, called The Road to Reality. It's about yay thick, and it's a wonder. If you still like books, if you read stuff in paper, and this guy is so, this is what I started reading and I got into this. It's such an enthusiastic account of the magic of these numbers. And finally, this is like the long downward spiral. If you Google Wikipedia complex numbers, you're at the top of the iceberg, that you just get sucked into all of that stuff. So I'd recommend, if you're interested in this, follow these things up. I think the other thing, just to add to what I was saying before, is that all I can do is facilitate. People in the room can be checking up as I speak on their iPhones and Googling this stuff, and so there's no concept anymore of my having some knowledge which I disseminate to you. All I can do is sort of point you in a direction of and try to enthuse you a little. Now, what I'll be doing tonight is I've got a whole bunch of material. Well, I've got some notes. Say this, say this, say this. And every time I read this, I think, no, I want to do this in a different order. So I haven't really planned this stuff. One of the things I'd like to do is to convince you that complex numbers are just numbers. So what I was going to do is, here's a history of numbers. I'll talk about this. Okay, so some of this is questionable. These are approximate dates. Human beings have evolved to have 10 fingers, and we seem to be able to annotate things. The original number systems, I believe, people had this. The native Tasmanians reputedly have a system that goes 1, 2, enough, plenty. So they count up to that for some primitive cultures, this is enough. This is all the numbers they need, 1, 2, plenty. And you can do arithmetic on this. And I suspect numbers started off with these sort of concepts. And certainly in the English language, the concept of number didn't split off as an abstract concept early on, because we still have special numbers for counting small numbers of things like pheasant. We have a brace of pheasant, or I can't think of any other, a couple of something else, a trio of things. And initially, the abstraction of a number from the object you're counting was a huge mental leap. And the next one about, I promised myself when I said this I'd look weird and say 30,000 of your Earth years ago. There is evidence of tally marks of people notching on sticks to account for numbers of things. So this was a unary system. Just, if somebody borrowed, 3 cups of sugar from me, I could make 3 marks on a stick to record this. Okay. And then the next thing was the base 60 Mesopotamian numbers. Again, this is an example of I'm trusting a poll of the internet for these figures, and the things are disputed rather a lot. So 3,500 years ago in Mesopotamia, which I guess is Baghdad, is it? Iraq? I can't. That's yeah. They started with a base 60 system, which is such a good idea. It's got lovely factors. It's just such a good idea. And of course, this stuff still resides in things that we have 360 degrees in a circle. It's still 60 minutes, I suppose. There's still some bits of 60 still around. And then around 3,000 years ago, the Egyptians started with a base 10 number system. And all of these things were counting numbers. And they probably started from 1. They probably didn't start from 0. And the reason for that is if you're a shepherd counting sheep, you don't need a 0. Like, what do you call a shepherd with 0 sheep? Unemployed. Because So 0 is quite a strange concept. And the 0, there's quite a lot of dispute. Somewhere I've written various dates for zeros. Any ideas? When did 0 occur? There's various people claim to have zeros. It certainly appeared in the Mayan culture in Mesoamerica. The Mayans had a 0. And they were great. The Mayans were index origin 0 people. They were good guys. They counted from 0. The first day of the week was day 0. The first month of the year was month 0. They had really good arithmetic. There's an argument to say they've unearthed a 0 in Cambodia recently. The Khmer people have a claim to having a very early 0 in their system. And there's two uses of 0. You have to point out this is firstly as a number in its own right, which is strange, and the second is as a space marker when you're counting. If you're counting base 10, you need to. If you've got a number like 103, you can't just write a 1 and a 3 because that's indistinguishable from 13. So you've got to have some columns. So those two concepts may have come separately. So that's the 0. And then what we have here, we're now into a sort of, humanity must have sort of seen the way this stuff was going. If we have counting numbers and then we have a 0, and then we can probably start doing elementary arithmetic, basic arithmetic. So, if you give me 3 sheep and somebody else gives me 4 sheep, then I own 7 sheep. And I can probably figure out that the same mental effort will do for pigs and frogs and whatever else I have, so I can start to distinguish those things. So the next thing, and I think this is quite a big conceptual jump, is negative numbers. It's a big conceptual jump to go from the natural numbers to the integers. And this would have accounted, I can't think of examples. Negative numbers, you would... I guess if you're borrowing stuff from people, that's a good example of a negative number. I couldn't find a convincing account of where these things came. And then the Greeks, the geometers, were into doing geometry, and they were into the ratios of 2 numbers. So they were very keen on. They had all of this. They knew what 3/4 and 7/8, and they could do geometrical constructions to produce these numbers and work with them. And my understanding is the Greeks were horrified when they found that the rational numbers weren't enough, that there were some things. If you have a square, actually I remember doing this, I'm so clever, I remember doing this as an experiment when I was about 6. I did a mental exercise, and I proved to myself mentally that the diagonal of the square must be 1.5 times the side. And I measured it with a ruler. I was check this out, and it wasn't quite. So I got bored and went and did something, dug a hole in the garden or something. But the Greeks, it worried them that there were numbers that the rational numbers. There were numbers other than rational numbers. And then, so the next step in this number story is the real numbers, which fill the gaps in between the rationals. So we have, now we can do all sorts of arithmetic, which still, we can start in the real line and we can do stuff, and we wind up in the real. So for instance, we can divide things, we can take square roots, we can do a lot of polynomials and take the roots of them, and we're staying in this complete real line. And one of the things I'd like to say here, the very next step in this chronology is complex numbers. One of the things that people found in the... And where's the dates? I've got the dates written here. Actually, in the 16th century, people were worrying that some polynomials had you couldn't find the roots. Some, for instance, quadratic equations seemed to have 2 roots, and some had 1 root and some didn't have any. And this was clearly there was something missing here. And one of the strange things is we're quite comfortable with the real line, the real numbers. But actually, the work on complex numbers, mathematicians understood complex numbers before they understood real numbers. If you think really hard about what the real line is, it's quite difficult. And it wasn't until Richard Dedekind, if that's how you pronounce it. I had to find a YouTube with somebody saying Dedekind to see how to pronounce this. At the end of the late 19th century, he published a paper in 1872 where he had an analytic treatment of real numbers. And it's only since that time that we've understood exactly what the real line means. However, going back to the complex numbers, there was work on that solving cubic equations. There's some part of cubic equations where you need to dip into, a cubic equation has a cubic polynomial has 3 roots, and you can get into situations where you need to dip into non-existent, imaginary, weird numbers as part of the solution and then come out again. And people were worrying about this in the 18th century. There were people like, I think Caspar Wessel, I'm not sure how you pronounce that, was worrying about this, published something in 1797. Oh, no, much earlier than that. There's Girolamo Cardano was writing about complex numbers in 1545. So this was really early on, and that was to do with the solution of cubics. Yeah. Okay, where are we at? Yeah. Now, one of the things that Penrose talks about in in his book is the magic of complex numbers. One of the things with the reals is what you can't when you start from the Greeks' position with the rational numbers, and you find that if you measure the circumference of a circle and you try and take the ratio of the distance round a circle to the distance across it, you can't find an exact rational number. And that bothered them. And the difference between the real, and also if you try to do my experiment and figure out the ratio of the diagonal of a square to its side, you can't do it there's not a rational number approximation to this. Now the thing about the reals, the thing about the complex numbers, and what we used to, if we've been using complex numbers, what we're very used to doing is to think of the complex plane. We're used to seeing this 2-dimensional, 2-axis representation of the complex plane. But for a long time, people didn't have that mental model. And what they said was it all narrowed down to, we can't give you a square root of a negative number. In particular, -1 doesn't have a square root. And all you need to do to generate the complex numbers is to think of the real line set with its infinite numbers, its infinite number of numbers, and you need to put one extra number in there, just one extra number, which you can call anything, which you define to be the square root of -1. And if you add that one number to this infinite set, then everything else drops out. The whole of the complex arithmetic drop out with the definition of this one number. And what Penrose says is that you can't do that with a real line. If you just put pi into the real line, that doesn't give you the square roots of things. If you just put the square root of 2, that doesn't help you with the 7th root of 19. So really the complex numbers are a much simpler system. All we do is we take the real line and we add one extra point in it, and then we can do our arithmetic. Yeah. So that's what I want to say about this. This is what I've learned with talking to people is it's what you send them away with that they remember. So we can go through all of this stuff, and then I'm going to show you a really cool conference giveaway. So that's the only thing you'll remember. So there's all this history will go in. All right. So that's probably, this is 3, so that's a history of numbers. And somebody was asking earlier about, does this go any further? And I forget who was saying about quaternions and octonions. Yeah. This story, mathematicians are never satisfied. You know, they constantly clearly there's an obvious generalization. If the real numbers are on a line and I write complex numbers in 2D, what about 3D? What about 4D? What about 5D? Clearly, it's an obvious thing to think about. And this story goes on actually just 2 more steps. It goes on to, I've got the exact date here. It's the 16th, I can't see it now, 16th of October the 16th, 1843. The Irish mathematician William Rowan Hamilton was walking with his missus along the canal in Dublin, and it occurred to him what the next step in this series was, and they were quaternions. And it was like a religious awakening, and he was so enthused by this that he carved the defining equations for quaternions on Broome Bridge in Dublin. Whereas with complex numbers, we just have to have I squared equals neg 1, and that's enough to generate the whole of the complex set. And the quaternions, you need 3 more. As well as an I, you need a j and a k, and the defining equations for this are I squared equals j squared equals k squared equals ijk equals neg 1.
Well, the interesting part of that story is that the mathematicians were baffled up until that point because they thought that there were 2 imaginary parts to quaternions, but the equations didn't make sense.
Yeah.
What came to him on that day while he was walking along that canal was that it wasn't 2 imaginary parts, it was
3. Yeah.
And that was the epiphany.
Yeah, and it was, and that, I've been tempted to go, we spent some, Flora is a dub, Flora's Irish, and we spent some time in Dublin, and I intend to make, the local mathematicians make a pilgrimage to this bridge every year. I think the original inscription's worn away, but they've got a plaque with this on. And in fact, when I was researching this, the quaternions were big in Dublin. Apparently, if you took an engineering degree in Dublin or a maths degree, the quaternions were a required part of the course for a long time. I think, and this is where my maths runs out, there are other techniques which are more flexible. They've sort of fallen into disfavour a little bit. And at the same time, the next level is a thing called octonions that Hamilton's mate came up with at about the same time. And somebody else, one of the names, Cayley, is it Arthur Cayley? Arthur Cayley published at the same time. But I found a statement somewhere that said this stops then because it says, and I don't understand what these words mean, there are only 4 composition algebras. R, the real numbers, the complex numbers, the quaternions and the quaternions and the octonions. So that's where that story stops. And somebody was saying to me, so you're doing complex numbers. While you're at it, why don't you put quaternions and octonions in at the same time? And there may be an argument for doing that. My feeling is we should live with this for a little bit and see. Once we put one data structure in, it's easy to do that. I think Morton's comment was very good. Of the people in this room, possibly 2% will find a use for complex numbers. I hope not. I hope you play with them, but in a real application, maybe 2% of you will find a real application for complex numbers. of that 2%, possibly 2% of those would find an application for quaternions and so on. So it's a little bit diminishing returns. Yeah.
Somebody made a comment about these quaternions being relevant to quantum computing.
Yeah, I've got a note here. Oh, quantum computing. I hadn't heard that one. It says I found that quaternions. Clearly, one of the things that complex numbers are good for is it's very pleasant to do 2D graphics. You can draw polygons, and you can rotate and transpose them using very simple complex number arithmetic, and the 2D graphics uses those. Apparently 3D computer graphics uses quaternions. There's some nice ways of expressing 3D graphics, and I'm just going to read this out, and they're jolly good for special relativity, modelling Minkowski space. So some of the people here will know all about that, but on my maths, I was away that day. Okay, and octonions are used apparently in string theory, special relativity, and quantum logic. You're right, yeah, quantum logic. So there is a market for these things. Yeah. Some people will have seen Roger's presentation this afternoon on the implementation. Roger Hui has been implementing the complex numbers in Dyalog, and it's just done a superb job, because the trick with these things, or one of the tricks, is the edge conditions and handling large numbers. As did some of you. I guess some of you were in Roger's talk, so he's done a superb job in this. Now let me. Oh yes. Okay. So applications. What are they good for? The 2D graphics is one. The electrical engineers use them to model AC resistance, impedance in AC circuits, and that's well established use of complex numbers. And there was an APL when Jeff and I were doing some of our. Where's Jeff? Where's Jeff? Big. Oh, geez. We did a port to the VAX. In the old days, we couldn't afford a VAX. I mean, if we wanted a VAX now, Morton would just buy us one. But in those days, we used to have to go and beg time on VAX. And somebody who lent us time on VAX was a guy called Bob Spence, who was an APLer, a British APLer of old. He was the prof of electrical engineering, I think, at Imperial. And he'd written a textbook on resistive circuit theory using APL as a notation. He wasn't trying to sell APL, he just said, this is a good notation for describing these processes. And I don't think any of the APLs had complex numbers in those days. I don't know whether he modelled them, maybe he emulated them. What are we doing for time? Oh, cheapest, how did that happen? Oh no, half an hour, right. I was frightened. Yeah, the other thing I'd like to say, what I'll do then is just show you the demo, and that's really cool, so you'll forget all about this. The other thing to think is, this is just I suggest you use this as a mental model. When you're thinking about complex numbers, and there was a quote, and unfortunately I didn't write down who said, Girolamo Cardano in 1545 said, this complex number is not a pair of things, but an entire thing on its own. And we sort of, if we see complex numbers written down, we see something like 1, 2, 3, J, 4, 5. But the trick is to think of that as a single. It's a single number. It's just a number. It's not anything. It's not a pair of things. It's just a number. And the standard, the extended standard, refers to numbers. It says in the APL, the left argument of reshape is a numeric vector. If it's not a numeric vector, signal domain error. If the imaginary part is not 0, signal a domain error. So the standard correctly, beautifully, just describes these things as numbers. and it restricts the range. So I lost my train of thought. Just a number, okay. Okay, now what I'm going to do now is so I'll just show you this cool little program, and you can take this. Let me just see if there's anything else. Oh yeah, here's... we've done that. Yes, can I recommend that what I'm about to show, just before I forget, we've emulated, we've been playing with complex numbers. If you want to pursue this, there's an emulation in the Defense workspace, which you have on your, if you have Dyalog APL, if you load the Defense workspace, there's an emulation of complex numbers. So until we produce V13, you can play, there's two things. There's an operator that will emulate complex numbers, and then there's a little complex shell that you can type complex numbers expressions in, and it's just a quote quad execute loop that goes around translating what you type into complex numbers. And you can start by if you click on it, you can watch it on the internet. The Defense workspace pages are on the internet. Yeah, and somewhere I had. No, this is okay. That's all I want to do. Right. So, what did I do there? I hit return. Okay, that's always a dangerous thing to do. Right. So I'm going to do this. Okay. This is just a little GUI. When I was Roger had pointed out I'd made some mistakes in this emulation. One of the things with, let me show you this first. I needed this little tool to play with, to check some things out, and I just got carried away with it. And I've been sitting in front of, when I'm supposed to be watching the soap opera on TV, I've been playing with this. So what this is CX. So what I'm typing in here is a complex expression. Omega is a number in the standard sense. It can be a complex number. And when I hit return as a GUI, I'm not really a GUI programmer, so I was pretty impressed that I could draw a circle in a box. But you guys do that all the time. I'll tell you the other thing that's really strange. What I'm going to do is use the mouse to point and click on this and draw things. And what I discovered was, I write with my left hand, so if you give me a pencil to draw with, I can draw badly with my left hand. If you give me a mouse, I use my right hand and use that badly. And I can't draw with a mouse with my left hand, it has to be a pencil. So, and this I didn't discover this until just now. I can't, so I'm going to draw very badly on this. So what this what this application does, it takes this function, and the plus for a complex number is the conjugate. What it does is if I click here, it draws a blue marker where I click, and then it applies this expression to the point in the complex plane, and it draws a red cross on the result. So that's the domain and range. So what the plus does now, in Dyalog before, plus you could always rely on that being an identity. If you said +3, it would say 3. But when we extend to the complex set, plus has a defined, it gives you the conjugate, the flip of the number in the real axis. It flips it in the real axis. And so if I just click some places, you can see it's just mirroring where I click. Yeah. And the other thing I can do with this is if I clear this, if I hold the mouse cursor down and draw, I get a continuous function. So what this is doing is showing me, it allows me to explore this function. Okay, so that's a very simple function, but it's just a way of visualizing a complex function. Because when we draw, we've got this nice Descartes invented this system. If I've got a function of reals, from the real line to the real line, I can put two real axes perpendicular to each other. So if I want to see what x squared looks like, I can draw values of x along the horizontal axis and values of x squared upwards, so I get a nice parabola shape. The problem with a complex function is you people just live in 3 space. So I would need 4 space to have the equivalent in for a complex function. So this is a sort of compromise of see, I can use this to play with a complex function. So that's a very simple one. So the next one I want to show you is reciprocal. Now, what are the things I can do here? So what must be the case is that reciprocal must work the same as it has on the real line. Oh, sorry, I didn't explain this, but you probably guessed. This is a unit circle. I'm not clever enough to draw markers on here, and it sort of obscures it. But this is meant to be the real value 1, and this is the real value neg 1, and this is plus I, and this is minus I. So if I take the reciprocal function, if I double-click somewhere near 2, then you can see I've got the reciprocal of 2 is a half on the real line. There's no that's not a surprise. And the reciprocal of something near 1 is just the other side of 1. But the interesting thing comes when I click on the complex plane, and what I'll do is clear this and start drawing a picture. So if you watch the red line corresponding to the blue line, it's down there. But as I come up to the complex plane, this is what the reciprocal function looks like in the complex plane. And you can see values outside the unit circle map to values inside. But if I draw, and values inside map to values outside. So it just extends beautifully from the real number, it just generalizes. And I was telling my son, who did an engineering degree, this, and he said one of his lecturers had this joke that he told over and over again. And it was, how'd you catch a lion in the desert? Because the lion's the same color as the desert, so it's tricky thing to do. And the answer is really easy. You draw a circle in the sand, not where the line isn't, and then you just invert the complex plane. So the line is then inside the circle you've drawn. So any points outside map to inside, any points inside map to outside. So what I'm going to do is just show you some interesting functions, and then we'll have some questions, and then we can go and drink some beer. So let me show the next one I want to show you is the square root. So this is omega to the power, the reciprocal of 2, or 0.5. Okay. So this is a square root function. So again, if I clicked near 2, you'd expect 1.4. Oh, what I should point out is if you look at the top of the caption, you probably can't see that, but it's showing me the coordinates. I can't really make that any bigger for you, but it tracks the blue. The thing on the left is where the positions of the blue part of the domain, and it maps to the right thing. So this one says 1.97J 0.03. A question I get asked a lot, people like, it's right up there with what's your favourite flavour of yogurt. I get asked a lot. People say, what's your lucky number? And up until recently, I've been saying 7 because that's That's safe. But just recently I've been saying 3J4. 1.2 E neg 7J 4.3 E108. And I've changed my style a little bit. Because it's just a number. So this is a square root. So again, if we clear this and we can start investigating this. So the square root, so what we can see here is as I go round the circle this way, let me start it, let me cheat a little bit. Right, so I'm going to start here, and it's a race. You can see the red line preceding me, but because I'm doing the square root, it's going half the speed, and when I get to here, we're back on the real line, so the square root of what is that? About 1.4 is somewhere in the 1.2 region. And I go around, so I've lapped this guy. Now, what's really strange is that when I get back to... Let me just take the mouse off a minute. When I get back to here, this line's got to get back to there, hasn't it? Yeah? So we've got a real problem here. Let's see what happens. So what I'm going to do is just I'm going to go here, and I don't know if you can see, it's jumped. Yeah? It's a warp, space warp, yeah. So let me just show that again. So as I come down here, I go the square root of, I'll tell you what, let me try and come down to the square root of -1 is I, as we know, because we defined it. And then when I jump down below that, I get to the negative I. And when you are implementing, one of the things that Penfolds, when you're implementing complex functions, they have things called branch cuts. And an example of that, I suppose, is things like, there must be an example in real trigonometry functions, are there, of jumps like that? I can't think of one.
And don't you have 2 roots for the square root?
Oh, yeah, okay, yes, sorry, that's a very good point. Yes, the square root should have 2 values. So the square root of 9 is either +3 or -3. Both will work as a square root of... That's a really good point. But APL defines, will give you, it chooses one of those arbitrarily, as it always has done. If you do square root of, in just boring standard APL, if you do square root of 9, it just chooses one. And in general, if you take the nth root of something, you get n possibilities. So there are usually 3 cube roots and 17 17th roots, but the APL language defines just the principal root. And what this is, the roots are arranged radially equispaced around a circle, and APL chooses the one that's closest to the positive real axis. Can somebody jump on me if I tell an untruth here? Because I think this is right. It chooses one. And one of the things, when you switch to complex APL, in the cube root of... Now let me get this right. If you type -8 to the power divide 3 in a regular APL session, I think it will say -2 at the moment. But actually, there are 3 roots, 3 cube roots of 8. One goes off in... Use the mouse. One goes off in this direction, -2, but there are 2 more equispaced around here somewhere.
Try your function with -3 versus 3.
Hey, what? Yeah, that's dangerous. So, how do we get to this cube? So, if I do the cube root of negative... I'll tell you what I'll do. I can ramp the scale up a little bit. If I put an 8 here, let me put a 10 for good measure. That just zooms out a little bit. So if I go around to the cube root of, that's around -8, is here. Yeah, it's in that quadrant. And I guess, is that... And if I go slightly below the line, it gives me the one. So there are There are 3 roots, and it gives me the principal root. And that's, if you change into complex APL, the only difference the only thing that will break your code is if you take an odd. This is not quite the story. If you raise something to the power of a negative rational number, Jeff knows this, with an odd denominator. So if you did 8 to the neg 2/3 or 5/17 or something, real APL, classical APL, will give you the real root, and complex APL is obliged to give you the first one it finds when it does an anti-clockwise sweep.
Oh no, my code's going to break now.
Yeah, no, all those, yeah. But some of these are quite beautiful. If you, oh yeah, so I was saying about branch cuts. So some of these functions have discontinuities, and you have to, when you're playing with these things, you can discover these. So that was the square root. But it's really interesting. One of the things you can do then is, for example, to investigate with this little function, it's good to draw little circles around interesting points. This is a branch cut, so this is a discontinuity there, but there isn't one. That's continuous, and that's yeah, because square roots near 1 plus 1 are near plus 1. And the other thing this does is, which is interesting to try, is if you draw the square root, if you draw a straight line as straight as I can, it's sort of really cool to see what that maps to. Yeah, it's fun, isn't it? It's beautiful. And the other thing it will do is if I try to draw a rectangle, you can see that there's a rotation involved in its mapping, its square root mapping. So I promised myself I'd try and do this. Here's a little circle in this with a couple of inner circles. Yeah, and you can see this is rotated and squished down. Yeah, that's a square root. A duck, oh, yeah. I can do it. I can draw a duck. Let me see. A duck's a 2, really, isn't it? A duck is just a 2. There you go. That's a duck. Oh, it's a swan. Okay, well, yeah. I'm a swan. Yeah, that's the best. Peter Donnelly could have done that in his sleep, but there we go. So let me show you a couple more. Some of these functions are quite interesting. This function is, and I wrote it down because I can't remember. You know, there's some of the circle functions are really interesting. They've got so omega, the 8 circle. And this is the one that Roger pointed out that I had wrong in my emulation. These are the sines and coses. Sine is 1 circle, cos is 2 circle. That's as far as I remember. But some of these have been extended. Some of them are things like the square root of the number you first thought of added to something else. This one I think is, 8 circle is something like, what is it? It's something, I can't remember. We can look it up in a moment. Okay, but Roger pointed out this guy has 2 branch cuts. It's got a discontinuity here, and it's got a, oh, hang on. It's got a discontinuity here. Let me just do that again. So there's a discontinuity. Can you see that jumped from here and here? And what I found, and this is beyond my maths to comprehend this, but if I make, let me see if I can do this. If I make a circle here, let me see if I can, oh no, I won't have, let me try again. I guess we can go inside the unit circle. There's something very deep about this. If I draw a circle here, if you look carefully, I haven't drawn it very well, but these 2 circles have got a twist in them. They intersect somehow. I can draw an open blue circle but when the red circle, let me try one more time so you can see it more clearly. The red circle, I spent hours playing with this. Now, let me go, which way am I going to go? I'm going to go here, so I haven't crossed the line yet. Okay, you can just about see them. And can you see these two circles stay in track, but they're obliged to, the red circles are obliged to cross each other. And there's got to be something very deep about that. I don't know how to explain that. But it's... yeah. So you can take I can give you this little program. This little program we put. Of course, it's a DFUN, and I'll put it in the DFUN's workspace. It needs version 11. At some point, I'm going to convert the DFUNs. When we ship version 12.1, we will retire version 10.1, and I will move the DFUN's workspace into 11.1, so I can use all the cool language things in there, like monadic commutes and power operators and things. So this will go there then. But we'll put this on the website so you can see it. I've got two more to show you. This one, okay. Can anybody except for Phil Last tell me what that expression does? Oh, that's the answer, yeah. Okay. Yeah. It just squares something. It's a multiply commute. It's a product commute. It just squares something. So it squares the thing to its right, and it's just a way of avoiding some parenthesis. So if I take the 1, 2 circle, spelt circle of omega. If I take this is a sine of omega and the cos of omega, and I square them, and I sum the result. So this is sine squared plus cos squared is this function. Anybody know what sine squared plus cos squared is? Yeah. So when I draw this, or let me just click. If I double click here, you can just see a red line on the... Can you see the red line there on the 1? And in particular, if you look at the caption here, you can just about see this. This, whatever number this is, maps to 1.00J0. It maps to 1. So if I draw a thing here, you can see the caption changing at the top, but all of these points map to 1. So even in the complex plane, sine squared plus cos squared is 1. Real 1. What I've got probably 1. Yeah, here's a good thing. I think it's really, this is the best thing you're going to get at this conference. Here's another one. This is a wonderful function. This is the exponential function. And what is strange here, here's a game you can play. So this is e to the something. So if I do e to the, I'll tell you what, let me make this a bit bigger. Let me zoom out to an 8. There's got to be a good word. The radius of this square is 8. There's got to be a better word for the radius of a square. Right, so if I click on 1, the exponential of 1 is about 2 3/4, isn't it? It's e to the 1 is 2.7182818 something. Yeah? So that's not a surprise. But what is perhaps a surprise is that if I start drawing this, you can see, it's gone way off to base, but it's going to come inland a bit. Right, here we are. We're coming in a bit, and we're coming down to e to the 0 is going to be 0. No, 1. E to the 0 is 1, yes, sorry. Yeah, and then we're going to go negative. And then as we go negative, e to the negative number goes towards 0. Yeah? So an interesting game. With little kids, here's an interesting game to show little kids. Actually, it quite amuses me. Have you ever seen this done? Hang on, I'll get it this time. Let me get it this time. Hang on, give me one. You can do that. Now, an interesting equivalent here is to try to make these lines. If I start here with a blue line, try and catch the red line. Oops. Well, e to the something, you can't. What we're saying is e to the something is not going to be the same as something because it blows up. Or so I thought. But it turns out that if I explore around here, I can make these lines collide. And where they collide is a fixed point of the exponential function. This has a property that e to the z equals z. How cool is that? And there's another one on the other side, of course. This thing's symmetrical. If I can, this is a bit of a... And I couldn't find it. I tried to find an analytical solution to e to the z equals e to the z, and I couldn't. So I just Googled, and they told me where it was. And I believe there's another one. Let me see. This has gone a bit. Whoa! This gets very. Where is this? Maybe I've got to go up. No, go. Whoa. So, no. We'll be here all night. Hey, there's another one there, and I can't remember. Roger, do you remember? Are there an infinite number of these? I can't remember. Sorry.
I don't remember.
You can't. We looked these up because I found this and I was emailing Roger saying, "This is so cool. What is that? What is this all about?"
You can expand e to the z as 1 plus z squared over 2 plus all the way down to z to the n factorial.
Well,
So you take away the...
I'd take away the number you first thought of. I tried to do that, and I wasn't clever. I missed a trick. You can expand these things. The exponential is, I think, 1 over... What is it?
1 plus z.
Well, it's z to... you can start from 0. You can say z to the 0, which is 1, over 0 factorial, plus z to the 1 over 1 factorial, plus z to the z to the n over n factorial, I think. Is that...
Well, yeah, so that the z is the second term of that infinite series.
Yeah.
So you have to, that becomes another infinite series. So
Yeah, I try to, because there's a trick you can use with infinite series. If you multiply, you get two of them in a row, and you multiply one by something, and then you shift them so similar terms line up, and subtract them, and there you are. And I wasn't clever enough. I couldn't find a way to do that. So there may well be a... But isn't that cool that there are fixed points of the exponential function? And the log function, I think there are an infinite number, a countably infinite number of fixed points of the exponential function. I think the log function, there are also fixed points, but I think there are just 2 of those. So, you can play with this stuff as well. So I'm nearly there. Oh, goodness, I'm running out of... so I'm nearly there, so that's good. So this has a little tweak in it, this program. Let me start again. Let me draw a fresh line. If I use CX draw and I've got an alpha in here, well, let's say omega times omega. That's just a square function. We could do that, but it's not very interesting. But if I add alpha to there, and it's not clear what this means. This starts a different mode. There's a little guard in this function that says, oh, I've got an alpha here, do something completely different. And what this is, it spatters grease on this piece of paper. So when I move the mouse over it, this mouse is just a piece of charcoal that I can draw on the paper. But when there's a greasy spot, no drawing comes out. And what I promised myself I'd do this. I don't really have the chutzpah to do this, but I'm going to do it anyway. Could I have a volunteer from the audience? I promise not to embarrass you. Anyone with a fine arts degree that would... What I need is somebody to come and continue the shading. Because if you shade round here, you can discover there's a shape here. It could be that it looks a bit like the coast of France. Will somebody come out and just do some shading? Come on, somebody must be brave enough. I'm going to pick on my wife if nobody steps up, and that'll be trouble. Good, yeah. Hey. Okay.
Show me what to do.
So all you've got to do is use the mouse in whichever hand you like and just wiggle and try and figure out where it's drawn. If you go over here, it won't draw.
Right.
But see,
it's
try and
straight
find where
on
the
in.
boundaries are of this thing. Try and find that out. Yeah, it's like there's nothing here. You'll get the hang of it. So just try and figure that out. You don't need to press anything. Just wiggle and just wiggle. Yeah. So I'll tell you what's happening here. What the program is doing inside is it's responding to mouse move events. And it's going as fast as it can. Every time it's polling the mouse saying, where are you? It sets that value in alpha. Yeah, so wherever it is in the complex plane, it's setting alpha to that value. And then it's iterating. It's taking that value and it starts with omega. It takes that value, and then it starts with a value of omega of 0, and it says omega times 0 is 0, add alpha, that's the next term in this series. And then so the next value is alpha, it's got alphas in here, so it's doing alpha times alpha plus alpha, and the next time it's got that number squared. So the first one is z is set to alpha, the next one it's set z1 is set to z0 times z0 plus alpha, and the next one z2 is z1 times z1 plus alpha, z2 times z2 plus alpha. And what this does, it runs it does that iteration a large number of times, actually 10. And one of two things happen. This series either goes off to, well, actually outside this picture, or it stays within this picture. And then what the program does says there's one of two things. It either has disappeared off the edge, or it stayed within inside. If it stayed within inside, the program goes back to the original alpha and draws a dot, single dot there. Otherwise, it doesn't. It could be the coast. I was thinking, wouldn't it be cool if this revealed the face of a religious deity? Like, wouldn't that be cool? Yeah, and you might, Diane, you might want to try. You might want to try a little bit over here. There might be some stuff.
I noticed that.
Just near the line. Yeah.
I thought it was supposed to stay in.
So, does this remind anybody of any? It's the Mandelbrot set. So the definition of the Mandelbrot set is exactly this. It says you take this sequence, all you do is for any point in a complex plane, it's in the Mandelbrot set if this sequence, starting from 0, you square it, add alpha, square that, add alpha, square that, add alpha, square that, add alpha. And if that stays within limits, within the area you can see, you draw a dot. Otherwise, it'll shoot off and draw nothing. Okay? I think that's really good. So we can see that's the Mandelbrot. Thank you so much, Diane. Yeah, way, thank you. Yeah. And just to finish, here's a proper one that Ray, Mr. Mandelbrot Cannon, lent me. So that's what it should look. So if everybody could sort of look, if we could all go like that, wow. You'll see. Ray has written this he's emulated complex numbers, and Ray's been writing these beautiful things for years. And actually, it's good to see this. No disparagement of Diane's efforts, but Ray draws it a lot quicker than. Let me see this, which is. So if I stop this, how do we do that? Actually, just loading it again would be good. What Ray does, the quad LX expression scans this area. Yeah, this takes about 1 second, so you have to be sharp when it comes up. And it's doing that iteration really, really very, very well. But Diane did a pretty good job of doing that. So that's Mandelbrot. And I think we've got. Okay, that's all the material I have. So, are there some questions about the? Any questions? Any questions? No? So in that case, you can take this CX draw program. It's really fun. As we encourage you to play with that, it drives your spouse nuts. I really wish I hadn't said that. I could be sleeping in the car park tonight. You can pick. I'll give you a copy on a memory stick, or you can just wait for it to appear on the conference materials. So, thank you for your attention. Thank you very much.